Hello and welcome back to the channel. In this video, we will talk about activation functions. Activation functions are one of the more core concepts of AI and machine learning. In this video, we will understand that why activation functions are needed, what are activation functions, and we will go through the various commonly used activation functions. So let's first understand why activation functions exist. So basically, in neural networks, weights perform a linear transformation that you can see here. Now, this linear output cannot model like complex patterns, right, on its own. So activation functions are applied on top of these linear transformation. Activation functions are applied to transform this like the linear signals into complex decision boundaries. So these activation functions enable like basically input to the next hidden layer. They are applied from one hidden layer to the transformation of the other hidden layer, and they basically enable non-linearity, depth usefulness, and complex decision boundaries. Let's take the example of a simple perceptron, right? You have a simple perceptron here, right? And this basically creates a linear decision boundary, a straight line in 2D or 3D, right? It cannot solve XOR, cannot model curved lines, curved boundaries, right? Now, why deep? Now understand that in deep neural networks there are a lot of linear transformations, right? Each in deep neural network, each hidden layer, right, a linear transformation is performed, right? You can see here weight 3, weight 2, weight 1, right? And this basically collapses into a single linear transformation. It can be, right? There are multiple linear transformation. You can collapsing it to a single linear transformation, which makes basically no sense here, right? Now activation functions prevent this basically collapse, right? Activation functions when applied on each of the neural network that you see here, like basically like let's say for example f is an activation function, it will be applied on w1, then w2 or w3. It basically transforms the linear transformation into non-linear and then gives it back to the w2, right? This basically helps in modeling complex decision boundaries to solve complex problems like image classification, sentence classification, right? So these are the two main important points that why activation functions are needed. There are a lot of others also. I have mentioned the basic two reasons that why activation functions are needed. Now let's understand each activation function one by one. The first is sigmoid function. The sigmoid function is given by this formula, right? Sigma x is equal to 1 by 1 plus e to the power of minus x, and its derivative is given by this, right? The graph looks like an S curve here, and the output range of sigmoid is basically in the range of 0 to 1, right? Where it is used, like the sigmoid function is majorly used in the area of like binary classification, and the algorithm where it is used is logistic regression, or it can be used as a output layer of any hidden layer of any hidden layer also, right? Understand that when it is used as a binary classification, this basically becomes a probability. Like let's say for example I am trying to classify between cats and dogs, right? One will lie towards like dogs and zero will lie towards cats, like kind of a probability, right? Probability interval of 0 to 1. Now tanh is another activation function which is frequently used, and we need to understand that. First of all, tanh is given by this formula, and its range lies between -1 to 1, as can be seen with this particular graph. While tanh is better than sigmoid, it has got zero-centered outputs, stronger gradients than near zero, and it has got faster conversion than sigmoid. How tanh is used in LSTMs, it's very important to understand, as LSTM is one of the basic algorithms in deep learning networks. Let's see here. In LSTMs, there are four gates like forget gate, input gate, cell state update, and output gate. If you don't know LSTM, please comment in the box. I will try and explain it in the next video. Understand that forget gate is basically the output of a sigmoid function, right? It basically tries to either keep or keep everything or forget completely the information. The input gate is basically means that how much to write and what to write, and here in the cell update memory you can see the tanh here. The tanh lies between -1 to 1. Basically the information will be processed, and how much information needs to be kept is decided here. In the cell update or the actual memory fold, the old memory is after basically thrown out after forgetting, and new memory is filtered. And in the output gate, finally we have again the sigmoid function, like what part of memory becomes visible, and then on top of it the tanh function is applied, right? So tanh as an activation function is very important. Now why tanh is ideal here? Because it keeps the values between -1 to 1, right? And it prevents exploding memory values. Now the major disadvantage of tanh to understand is that it still suffers from saturation and vanishing gradients in deep forward networks. When to use tanh? Tanh is used when zero-centered signals matter. It is majorly applied in the area of RNNs and LSTMs and modeling sequential memory states. The next activation function that we would like to talk about is ReLU. Like the ReLU is given by this particular formula, and its values lies between the area in the range of 0 to infinity, right? And its graph is given by this, like you can see here, like either the values which are greater than x, you will have in a straight line here, like if it is x is equal to 2, it will be 2 here, x is equal to 4, it will be 4 here, and it will go on. Or if it is x less than 0, it will be always be 0, right? And you can understand from the derivative also here, right? If you derive this ReLU x, greater than 0 is always 1 and less than equal to 0 is always 0. Where it is used in the area of CNNs, MLPs, deep forward networks. The advantage is basically computationally efficient, no saturation, sparse activation, and faster training. The major disadvantages of ReLU are dying ReLU, not zero-centered, and non-differentiable at 0. When to choose ReLU? ReLU is the default activation for hidden layers, deep architecture, vision, and general machine learning tasks. Now, one of the most important activation function that is majorly and frequently used in the final layers of any neural network is softmax. Let's say, for example, you have got 1000 images to classify, right? Yeah, the model basically takes in an input of image, right, and outputs that what is that image, whether it is dog, whether it is cat, whether it is shape, or 1000 different classes. What are you going to do then? You apply the softmax function. The softmax is given by this formula, right? And it is used where multi-class classification is done, right? Its output is basically applied in the area of final output layer. It basically produces a probability distribution. So if you have got like 1000 classes to classify, and that particular image belongs is a dog, then you will get basically a higher probability for dog. Like if this is class 1 for dog, and all others will get lesser probability. So that way you can choose, you can say that this particular image is of dog based on the probability distribution given by softmax. It works seamlessly with cross entropy loss, and it highlights a higher class confidence. What are the disadvantages? It is sensitive to large logits, coupled gradients, and not suitable for hidden layers. How to choose? We choose softmax only when classes are mutually exclusive and output represents probabilities. Mutually exclusive means that there is clear distinction, like image classification, sentence classification. These are the areas where softmax is predominantly used. Now, one important factor that I would like to basically put in is that if softmax, right, you can understand very well from here that if softmax, in case of softmax, like if n is equal to 2, like if we are considering only two classes, then we can see that sigmoid and softmax produces the same output, or you can say that this, when n is equal to 2, then softmax becomes a binary softmax, right? uh, but why we still prefer sigmoid in practice? Because it got fewer parameters, faster, cleaner laws, and basically the same result, right? You can see here, we have plotted a graph of sigmoid and binary softmax for the same data, and you can see that they overlap here exactly. So that's all we have in this video. I hope you like this video. If you like this video, please like and subscribe. In the next video we will talk about 4 more different types of activation functions. Thank you.